In this video, we'll be going over problem 9 in the January 2020 CXC Math exam. In part A, we're given a circle with points A, B, C, D lying on the circumference. We know that the angle CBD is 49 degrees, and we know that the angle OAB is 37 degrees. In part 1, we're asked to write down the mathematical names of the straight lines BC and OA. Since B and C are points on the circumference, the straight line BC is called a chord of the circle. The line OA goes from the center of the circle to its circumference. That's a radius of the circle. In part 2 of this problem, we're asked to find the angles X and Y and give our reason for how we got those answers. To find the angle X, we want to observe that both OA and OB are radii of the circle. Since those two line segments are radii of the circle, they have the same length. Now, if we look at the triangle AOB, since OA and OB have the same length, I can conclude that the triangle AOB is an isosceles triangle. Since we have an isosceles triangle, we know that its base angles are the same. So the angle OAB is the same as the angle OBA. We're told that the angle OAB is 37 degrees, so both of them are 37 degrees. Lastly, we know that the interior angles of a triangle add up to 180 degrees. So we can use that to find the angle X. We know that the angles OAB plus the angle OBA plus the angle AOB equals 180 degrees. Substituting the values that we know, we have 37 degrees plus 37 degrees plus X is equal to 180 degrees. So solving for X, we have X equals 180 degrees minus 37 degrees minus 37 degrees, which equals 106 degrees. To find the angle Y, we want to start by observing that the line BD is a diameter of the circle. This tells me that the triangle BCD is a triangle inscribed inside a semicircle. And whenever you have a triangle inscribed inside a semicircle, the angle opposite of the diameter is 90 degrees. Therefore, we can conclude that the angle BCD is 90 degrees. Again, we're going to use the fact that the sum of the interior angles of a triangle add up to 180 degrees. So the interior angles of triangle BCD sum to 180 degrees. So this tells us that the angle CBD plus the angle BCD plus the angle CDB is 180 degrees. Plugging in what we know, we have 49 degrees for the angle CBD plus 90 degrees for the angle BCD, and then plus Y for the angle CDB. This is equal to 180 degrees. We can solve for Y by subtracting 49 and 90 from both sides. So Y is equal to 180 degrees minus 49 degrees minus 90 degrees, which gives us 41 degrees. So that's the angle Y. Another way to find Y is by drawing a line from O to C. Notice that this line is another radius of the circle. So I have a radius here and a radius here, which means that the triangle OCD is an isosceles triangle. And its base angles are equal, so this angle here is Y. Now we can also look at the triangle OBC. Here, OB is a radius of the circle, and OC is a radius of the circle, so the triangle OBC is also an isosceles triangle. which means that its base angles are equal. So this angle here is also 49 degrees. Now let's consider the triangle BCD as a whole. I know that the sum of the interior angles add up to 180 degrees. Well, the interior angles are the 49 degrees, the angle y, and also 49 plus y. So we have that 49 degrees plus y plus 49 degrees plus y equals 180 degrees. Simplifying this expression, we have 2y plus 98 degrees equals 180 degrees. Subtracting 98 degrees from both sides, we have 2y equals 82 degrees. Then I can divide by 2 to get y equals 41 degrees. So this is an alternative way to find y. In part B, we have a diagram showing the route of a cruise ship. We have that the bearing of Q from P is 133 degrees, and the angle PQR is 56 degrees. In part 1, we're asked to find the angle W. First, let's notice that we have parallel vertical lines running through P and Q. Then the line from P to Q is a transversal line. From geometry, we've learned that if two parallel lines are cut by a transversal, then the pairs of alternate interior angles are the same. This means that this red angle here is the same as this red angle here. And also, this purple angle here is the same as this purple angle here. Since the red angles are the same, we can write an equation describing this relationship. The top red angle is 133 degrees. That is equal to the bottom red angle. The bottom red angle is the sum of 56 degrees and the angle W. I can solve for W by subtracting 56 from both sides. So we have W equals 133 degrees minus 56 degrees, or W equals 77 degrees. Next, in part 2, we want to determine the bearing of P from Q. The bearing of P from Q is the angle measured clockwise from north until we hit the line PQ. We can break this green angle apart into two pieces, the part from north to south, and then the part from south all the way to PQ. The portion from north to south is 180 degrees, and then the portion from south all the way to the line PQ is 133 degrees. So our bearing of P from Q is 180 degrees plus 133 degrees, which gives us 313 degrees. In part 3, we're asked to calculate the distance RP. To calculate this distance, we're going to use the law of cosines on the triangle RPQ. It tells us that RP squared is equal to RQ squared plus PQ squared minus 2 times RQ times PQ times cosine of the angle opposite of RP. In this case, that angle is 56 degrees. So let's plug in some of the quantities that we know. Well, RP is unknown to us, so we'll leave it as RP squared on the left-hand side. RQ is 290 kilometers. So we have 290 squared plus PQ squared. PQ is 210, so we have plus 210 squared, minus 2 times RQ, that's 290, times PQ, that's 210, times cosine of 56 degrees. So we have that RP squared is equal to 84,100 plus 44,100 minus approximately 68,110. So RP squared, when we combine the right-hand side, gives us 60,090. Finally, to get RP, we'll take the square root of both sides. So RP is equal to the square root of 60,090. If we enter that into our calculator, we get that RP is approximately 245.1 kilometers. So that's our answer to this problem.